Welcome to The Explainer. Today, we're decoding the secret language of chemistry. Now, I know that might sound a little intimidating at first, but honestly, it's just a hidden code that exists literally all around us. It's in the food we eat, the water we drink, the air we're breathing right now. And once you understand a few basic rules, it's like a giant puzzle pieces together, and a whole new way of seeing the world just unlocks for you. Okay, let's dive into this.
Here's a quick roadmap for today's explainer so you know exactly what to expect. First, the magic of compounds. Second, naming chemical compounds. Third, decoding chemical formulas. And finally, visualizing particle diagrams.
Let's kick things off with Section 1, the magic of compounds. We're going to start with a mind-bending chemical contradiction, one that actually sits right on your dinner table every single day. But first, let me ask you something. Think about this carefully. Would you ever, in a million years, willingly eat a highly reactive, explosive metal? Or how about taking a deep breath of a toxic green gas? No way, right? It sounds absolutely terrible. You'd never want to consume pure sodium, and you definitely wouldn't want to mess around with pure chlorine.
But look closely at what happens here. If we take those two highly dangerous elements, pure sodium and pure chlorine, and combine them, something truly magical happens. They completely lose those terrifying dangerous properties and transform into totally harmless white crystals. It's a brand new substance called sodium chloride, or as you probably know it better, just common table salt.
So how on earth does an explosive metal and a toxic gas magically turn into something you'd sprinkle on your French fries? Well, the secret is a process called bonding. Bonding is basically the chemical term for two atoms joining tightly together. It's the physical mechanism, like a tiny microscopic lock, that snaps these dangerous individual elements together to create entirely new, stable, and completely safe substances.
And that brings us to a really foundational concept in science. A compound is a substance formed when two or more different kinds of atoms are bonded together. So the crucial point is that a compound absolutely must have different kinds of atoms joined up. That's what makes it completely different from an element, which only has one single type of atom. When elements bond to form a compound, that new compound has a completely new identity and totally new properties.
Moving right along to Section 2, naming chemical compounds.
All right, so now that we know what a compound actually is, let's figure out how to talk about them. Just like learning French or Spanish, chemistry has its own specific grammar rules. But don't worry, they're actually pretty straightforward. Let's walk through the big three. Rule number 1, if a compound contains a metal, the metal's name always goes first. Simple enough. Rule number 2, if there's a nonmetal in there, its ending usually changes to IDE, or IDE. And rule number 3, when a compound has two different elements plus oxygen thrown into the mix, the ending changes to ATE or ATE.
Let's actually see this in action. Look at chlorine as an element and notice how it transitions to chloride. And this brilliantly illustrates our second rule. That tiny, simple change from an ine to an ide is a massive flashing signal. It tells us that the element chlorine has chemically bonded with a metal, like our friend sodium, and transformed into a compound. It is not just wandering chlorine gas anymore, it's sodium chloride.
Now take a look at these beautiful bright blue crystals. The chemical name here is copper sulfate. Let's apply rule number 3 to this one. See that 8 ending on sulfate? That acts like a giant scientific clue. It immediately reveals that there are actually 3 distinct elements hiding inside this one compound. We've got copper, we've got sulfur, and because of that specific 8 ending, we know for a fact there's oxygen locked in there too.
All right, Section 3, decoding chemical formula.
So we know how to say the names out loud, but how do scientists actually write all this down without it taking forever? Well, every compound has a chemical name, sure, but it also has a formula. Think of a formula as a quick, readable shorthand. It tells you the exact symbols of the elements bonded together in that specific compound. It's literally the written code translating a long, clunky name directly into the universal symbols you'd see on the periodic table.
Now, what's really interesting about this slide is just how much critical information is packed into these tiny little formulas. The letters themselves tell us exactly which elements are at the party, but look closely at the little numbers written slightly below and to the right of some symbols, like the 2 in CO2 or the 2 in H2S. We call those subscripts. They tell us exactly how many atoms of each specific element are inside one particle of that compound. So for carbon dioxide, that little 2 means there are precisely 2 oxygen atoms securely bonded to a single carbon atom.
But, you might be looking at calcium oxide, CaO, and thinking, wait, there are no numbers there. You really have to pay attention here. The golden rule is this. If there is no subscript number written next to a symbol, it just means there is exactly one atom of that element. It's invisible, but it's there. So, CaO is simply one calcium atom bonded to one oxygen atom.
Let's wrap things up with Section 4, Visualizing Particle Diagrams.
Okay, we've mastered the names and the written formulas. Now let's bridge the gap between letters on a page and how this actually looks in 3D space. Because atoms are way too small for us to ever see, scientists rely on models, like a physical ball and stick model. These are absolute game changers if you're a visual learner. They show you exactly which atoms are joined together. The different colored spheres represent different types of atoms, and those little sticks, those are the chemical bonds holding the whole shebang tightly together.
We can also draw these out flat to make them super easy to identify. Check out these 3 particle diagrams. On the left, carbon dioxide. One black carbon atom bonded to 2 red oxygen atoms. In the middle, water. One red oxygen bonded to 2 white hydrogens. Now, because both of those have different kinds of atoms joined up, boom, we instantly know they're compounds. But look at the one on the right, oxygen gas, O2. It's just 2 red oxygen atoms bonded to each other. Since the atoms are exactly the same kind, it's just an element, not a compound.
Let's move to and see how this builds our understanding with one final, perfect example. This is the diagram for methane. Try to decode it yourself based on what we just went over. You can clearly spot one central gray carbon atom in the middle, right? And it's bonded to 4 surrounding white hydrogen atoms. So if we just count them up, the chemical formula has to be CH4. It's a beautiful visual representation that perfectly matches our written shorthand.
We have successfully decoded the names, the formulas, and the actual visual structures of these incredible chemical compounds. So I want to leave you with this. Take a second and just look around the room you're in right now. Every single object you can see, touch, or hold. Your desk, your coffee mug, the clothes you're wearing, it's all just a combination of elements locked together in a secret chemical code. So what unseen chemical formulae are making up your everyday world? Keep asking questions, keep decoding, and thanks so much for learning with me on this explainer.